So here we are. I think we're past most of our core concepts, but we're getting to this, what I call the advanced concept 3. It's not a new concept. It's really about center mass, but I think it's a little advanced because the expectation here is to use calculus. And as I mentioned in most of these videos, I'm probably not going to be teaching math, but how you apply the concepts here and make your math problem easier to understand and hopefully easier to solve, right? So this is, you can see here it's 3a because I'm probably going to be doing B and C, multiple videos, maybe even a D, or just on center of mass. So that's the concept 3 that we'll cover in the advanced series. But we'll start off with center of mass for a lamina, but using calculus, okay? And that's really the whole idea of this video. And I'm going to try and illustrate a few different examples as well, and then leave you to do the integration and the math yourself. But we'll start with a rather simple form. We probably saw our pizza slice problem, right? We had our, and if this was alpha and this was alpha, I haven't made it symmetrical, but, and we also defined that, there is a center of mass here, which we defined as x bar being equal to 2 by 3. This was r sine alpha by alpha, right? That's sort of the lamina center of mass. And obviously we wrote it as a formula, but we want to try to investigate this a little more and see how do we end up, or how do we get to where we get. So I want to go back. I'm going to take this off. I'm going to go back to the basic idea, right? And this is what you should remember, because this is the foundation of how you set your problem up, right? So if you remember, as an extension of the moment function, the total mass of the lamina was written as a summation, right? I is equal to, say, A to B, and we'll discuss that in a bit, x times I and mass times I, where xi is the center of gravity or center of mass of that tiny piece that we took, and mass is that tiny piece, the mass of that tiny piece, right? So if you had and similarly, you probably write the same for y, as by extension, y would be times mass would be I equal to A to B yi. Now what I want to do is understand the mass here, which is the total mass. And I'd say if the total mass is nothing but the summation I equal to A to B of all of the little pieces of the mass, right? Now I'm going to start here by writing a simple function. Let me just say this is a function, some function where y is equal to f of x. And to make it simple, I'm going to define a boundary here, right, with an equation x equal to a and x equal to b. What I'm effectively identifying now, and you'll know from integration, that is the area, and that becomes my lamina. But how do I find the center of mass of that lamina? So this is the fundamental problem. And the problem, as you will know in integration, the way we would approach it is we take what we call an infinitesimally small piece, which is delta x, and that is at a distance of x. Well, rightfully, we would say x tilde. We would be able to plot this place because it's really tiny. We'd be able to come back somewhere here and define y here precisely as f of x, because we've moved x units away, and then we've taken a tiny piece. Now, we take this tiny piece to assume that it is a rectangle. If that's a rectangle, what would its area be? Its area, and I will use the term delta area, is nothing but this height y times delta x, that thickness. I want to introduce a concept here, and I'm going to write that down here with the symbol You'll see this a lot in physics for density, and this is really what it is. And this is really mass by area, or unit mass, right? The unit mass. But the same would apply if you were doing a wire in a framework. If it's just a wire or a rod with single dimension, this would be mass by length. And if it's a three-dimensional object, it's mass by volume, which is density, right? So if that's the mass, then I can come back here and write delta of mass is equal to rho times y times, and this is really, if this segment was my I, then this would be, all of this would be applicable for that tiny piece of mass at mi. This would be the tiny elemental mi. With me so far? We're still in the basics of integration, but I want you to get that conceptually. What are we doing with a lamina is really that, right? We're taking a tiny piece of that lamina in some measurable means. I mean, we'll see this now, we're doing it as a rectangle, but we'll also look at it as a triangle later, right? But we're taking a tiny bit here, and we're establishing that mass as area times densities or unit mass to get that tiny mass. Now, what would be the center of gravity of this one? Because it is fairly tiny here, center of mass for this particular one is very clear. We've got our xi, that's very clear, right? That's x tilde, right? But what would be y? yi would be, we know from this is y tilde by 2. Or actually, maybe I should, yeah, it's just y tilde, which is, that's y tilde is equal to y by 2. With me so far. So this is the rectangle. So I've spotted the center of mass here as half of y, and then I've taken it as x. And the reason why I can do this comfortably is because I'm going to set delta x approaching 0. So it becomes an extremely, extremely tiny value. There is no variation of x here. So you wouldn't say this is x, I don't think you'd say x plus delta x, the whole divided by 2. And there is no delta x by 2 because delta x is already tending to 0, right? So if I have this idea now, and then I bring it to integration, and you can see now what happens with this. This can be written as the integral from a to b. How do I write my mass? Unit mass times y times dx. And we know y is equal to f of x, so you can actually write this very comfortably. Now what happens to this side here? This side here would now become, I know this is nothing but x, so this would be the integral 0 to b, or rather a to b, sorry, the little mass and x. So I have my x and the little mass, which would actually be just the multiplication or the product of the density times, I have x coming in, which is really x tilde, writing it as x, times y, which is nothing but f of x, times dx. Now I have an integration problem in x. And this would now become integrate a to b, it's just y. The center of mass y is nothing but y by 2, and then multiply by mass. So I will write this, the density factor, mass is there, which is f of x, and I'm multiplying that with y by 2, so that becomes y square by 2 times dx. Again, y is equal to f of x, so this becomes a integration with x as the variable. Now that you know m, you can always get x bar and y bar pretty easily, right? So a general formula, and again, you can choose to remember this formula, but there might be special cases where it's probably not wise to apply it directly, but we'll get to that in a second, is the integral. And I'll do this and I'll show you what's going on here. Y, and the limits stay the same, but here it's mass. I have the density here, and I have a density here. That density can be cancelled out, and I can write this as just xy dx divided by y dx. And I can write y bar as, again, a special case, going a to b, same thing, density cancels out. This will be 1/2 y squared dx divided by a to b y dx. I've set this up this way. I just want to make sure you don't get confused and say, hey, can we cancel y out and just write it as y dx and integrate? No, there are two separate integrations that you'd have to do. You'd have to set them up and integrate them and put in their limits very, very carefully. So you make sure when you do your problem, it actually appears as this is f of x, so you're basically doing x f of x, integrated f of x, and you put in your limits a and b here, and likewise, this is just f of x, and then you will put in your limits a, b here. You are not, there are two separate integrations that we will be doing. They're not a single one, right? So this is an important idea to keep in mind. You can choose to kind of memorize this, but I think if you work it out yourself, you probably don't need to memorize, and if you do enough problems, you can remember this. But let me now extend this to a small hack that I think you should also keep in mind. There are many times when we don't need to worry about this integration, especially if you find a familiar area. For example, if I asked you for that pizza slice here, and I go back to my blue for my pizza slice, and supposing you knew that this was right angle is 90 and this was r, it would be fairly easy for you to say what is the mass, because really what I did here is I only did the area because the mass kind of cancelled out here, the unit mass cancelled out. And if you saw a quadrant of a circle, pi r square is the area of a circle, so pi r square by 4, you wouldn't have to do an integration problem of any sort to get the mass. So you would automatically know that the area is nothing but pi r square by 4 for total area, and then if you had to put in a density function, you'd do that. So it's a little hack. Keep in mind, that's why I wanted to go through them separately so you can appreciate what's going on. But in any case, what this is needed, it is two separate integration actions. It is not a single integration of the numerator divided and the denominator, because then you would just cancel y, or you would. No, we're not doing that. So pay attention to this. This is an important point to remember. Okay, now we will take this idea and extend it a little bit to see what happens and why I think the idea of the limits and understanding these limits becomes very, very crucial. But before we go there, I'm going to just take this concept and extend it a little bit to something very familiar, and we'll try to achieve that result just for you to get a comfort level, and then you can extend this concept to other shapes. Okay, so we're back. I have a very simple right-angled triangle there. I know this is a right-angled triangle. I obviously can determine a magnitude using Pythagoras, and that's not what is of interest to me. What is of interest to me is attempting the integration method here. And what I want to do there is take a tiny, the exact same thing I did, take a very tiny piece here, such that this is a rectangle, right? And obviously I have my dx, I know that. I know my factor y. I can define my x and my y tilde there. I know them. When I see this very easily, I can say this function is nothing but y equal to, what would be the f of x here? It would just be r by h, that's the slope of this line, r by h, times x, right? That's the easy function that I have. And if I just apply it here and then try to see whether I can mathematically arrive at an answer, what would I do here? I would simply say, hey, where's my center of mass? Well, my center of mass, well, first of all, what is the mass of this? Well, that's easy, because we know the area of a triangle, half base times height. So I have my density factor, whatever that is, half times base times height is just r times h. If I just did that. So this is an easy one. And if I want to do my x bar, what am I doing now? I'm basically setting myself up to integrate the little x times the mass here, the tiny mass, and I'm going to just write this as the integral, right? And this time I'm going 0 to x is equal to h, right? My tiny mass is nothing but y. Y is nothing but, first row, y is nothing but r by h times x times dx multiplied by x, which is the x tilde. So that's my mi and that's my xi, divided by r h by 2. So right away I have x squared, and I know that this would be x squared. So because r by h comes out, I could take out r. This goes away, the r goes away. So how would this equation would just become the integral from 0 to h of x squared dx divided by, and here all I have is, and here it's 1 by h, so that h comes down. I have an h squared, and I have by 2, right? This h is constant, comes back here, so there is an rh here. So that's as easy as it, and then the moment I try its integral, what is the integral of x squared? It is x cubed by 3, because the differential would be 3x squared divided by 3, which would be x squared. So this would be x cubed divided by h squared, and there's a 3 here, and this becomes 2. So 2 by 3 of x squared, x cubed by h cubed, with 0 and h as the boundary conditions. When this is 0, obviously the whole thing turns 0. When this is h, very easily this is h cubed by h squared is just h. So the answer would be very simply 2 by 3h. So it almost adds to our idea that if that's our h, and almost always you'll find this to be true, you'll end up with your center of mass 2/3 the way, right? So the center of mass on the x-coordinate is 2 by 3 h, and this is 1 by 3. Now, the reason why I want to be clear with the arrows is this is an area which they'll trick you with, because if you read the question clearly, you'd know, are they asking you for the distance of the center of mass from the base, or the vertex, or the apex, or the tip, or however they phrase your question? So pay attention to how you integrate, and that's where it becomes important, and that decides how you set the limits, which will give you the answer. So this is an important area that you need to keep in mind. I can do the exact same thing for y, or you can attempt it, but let's give this a shot just so we see what's going on. So y bar, right, which is here, right, very simply we know from our equations here, right, and I will write this as the integral. So what is y going to have as limits, right? This is the question. You might be tempted to say, wait, I'm going to do my y between these limits of 0 to r. So keep that in mind. That's a temptation, but we'll see where we're going, right? So for now, I'm going to follow the same rules here, 0 to h, right? And the reason why I'm doing it is because in my head, I'm seeing dx. So I'm seeing the increment of x. So I'm adding up all my x's. So that's how I'm seeing it. But let's see whether I'm right, right? I have my mass, unit mass, right? I have that, which is my tiny area, and I'm multiplying it with y. So I know that I'm going to arrive at r by h of x times my dx, which is my area and mass, multiplied by r by h 1/2 r by h x with me, and then I have my rho rh by 2. This hasn't changed very much, but this is really the mi, and this is the yi. These are the two components. This is a 1. So if I played with the math here, what do I get? I obviously take this out. This goes out. Nice and easy. I don't have an h anywhere, but I have a 1/2 somewhere. I have this 1/2, and I have a 1/2 here, so they go out. So nice and easy there. I have an r and an r that can clear out of the way. What am I left with? I am really left with, and I'll write it here, 0 to h. Watch what I'm left with. I have an r, I have an h squared, I have an x squared, and I have dx. And here, all I have is an h. So if I move this around and I solve this integral, it would be as simple as writing this as, so h cubed is in my denominator. I have an r. X squared I know is x cubed by 3, and I apply my 0 and h here as my limits. What was going to happen? If it's 0, all clears out, whole thing is 0, but if it is h, it's h cubed and h cubed, they go away, and I'm left with r by 3. So independent of this, I can safely say that when I integrate, it's somewhere r by 3, it's somewhere here. So this would be nothing but r by 3. And logically, you can do the math. If you do another mechanism of x and y, this is 0 and 0. This is h and 0. This is h and r. And if you sum the x coordinates, y coordinates, and divide by 3, you'll find out that the x coordinate basically is h and h by 0, h and h. 0, h, and h divided by 3 is 2h by 3. And the y coordinates 0, 0, and h, 0, 0, and r, 0 plus 0 plus r is r, divided by 3 is r by 3. So it also intuitively can tell you that if you have a triangle, the sum of its x coordinates and the sum of its y coordinates will be the average, not sum, the average of its x coordinates, average of its y coordinates will give you the x and y coordinates of your triangle, no matter the triangle, right? So I hope you're with me on that. So these are important ideas to remember. I encourage you to derive it yourself and so that you get comfortable with the functions. But we're going to now extend this a little bit to see what happens. So where are we? We've got that. We know the center of mass is for that one on top there, and I'll write that in blue, right? And I'll just say if this is 1 and this is 2, the idea I'm trying to bring forth is if I do x bar of 1, I knew very clearly that that was 2/3 h. And you kind of get the idea, 2/3 h, meaning it's tilted more to this side. There's obviously more matter here, so it makes sense. And if I did the y bar of 1, that was r by 3, right? 1/3 the ways of r, so it's somewhere towards this side. If it was 1/2, it'd be the center. So again, there is a tilt towards the part which has more mass. Now, what I want to do is I've created a much bigger triangle here. But what I want to highlight is with a line of symmetry. Now, my previous one didn't quite have. I could have made a line of symmetry this way and done it, but here I want to try and show you what happens when I have a mirror image and a line of symmetry about x. Now, I could attempt to do this again as an integration problem, and I encourage you to do it. This time you have a y-axis here, and you have another y equation here, but this y equation is basically written with the formula, so that's why I have another y. So I could say y1, this would be y2 would be equal to negative r by h of x, because when x is equal to h, this will be negative r because it's going on this side of the coordinate. I could write this, and then what you would do is basically extend this. You would extend this, and now you would have two pieces here. Your boundary changes, so you just cannot write. So there's no more an option when I do any of mine, because remember we saw the value for y showing up very conveniently when even at x bar we know that there was an integral 0 to h, and then we saw it's xy dx, because we took the density out and then divided by the density of the total mass. Now here obviously it's half base into height. Height is 2r, so it's just nothing but r by h. I don't even need to do this. I can just write r by h, right? Because that's 2r and that's h, and that's divided by 2, and that's area. So I could just write this very simply like this. But notice that this y, now what do? You got these two values. You would now have to write this as y1 minus y2 dx. And if you did, let's take a look at what happens. I like this problem a fair bit, and I hope this color is visible. Now, I'm not feeling good with it. I'm going to chuck this. I need something brighter. So I'm going to now write this as, okay, here's how I break it down, and I'll cancel my density. I don't want to see that again. So let me just write this as x times first one r by h times x minus, important to see how the next function goes, negative r by h is the slope, x dx. Now I have my r by h at the denominator that stays. If you can do the math yourself, but it's basically x comes out here, gets multiplied. This is basically an addition because this is negative, so it's nothing but 2r by h. So I'll take the 2r by h here. I come back to 0 to h, 0 to h. I'm back to my x squared dx, and I have my RH here. Now you'll see, if you remember, you'll see this thing coming up here. This is quite interesting. We'll continue this problem and just see where we end up with it. I'm going to take the r, cancel the r out, and I'm going to write this as 2 by h squared times, this is nothing but x cubed by 3 with 0 to h. What did I do wrong? I did something's not right. My y is correct. I have a full area. I think I'm right. I think I should be right. No, I think I made a mistake here. Because what I wanted is really x tilde, which is this x. I have that. I have the boundary of my y, so I've represented this as area that's there times x. So I think that's also right. So it's 2h by r. So I think I'm good with that. Yeah, so far it looks good. Right? So what would that give me? It would just bring me to 2h by 3. Ah, that is right. Which is similar to what I got previously. So nothing's really changed. On the x-axis, nothing really changed. Let's try to get to the y factor now. Let's say we have y bar, and this time I'm going to omit my mass of the denominator, just write that as r times h. And I'm going to write this as integral 0 to h. Okay, for y, it was 1/2 y squared, right, which was really half this value. And if you see, let me say area first. Okay, so that's the area would be y1 minus y2, that length, times dx. Now I need the center mass. This is nothing but center mass. If I just did this as the gap between the two, so it's still y1 minus y2 divided by 2, right? It's half, or the sort of the midpoint, right? So I'm doing this as a midpoint of a rectangle. So it's y1 minus y2. So I'm going to do y1 minus y2 as the length, divide that by 2, right? That would give me that y coordinate, and I multiply it by the area. So this would be squared, and I still have 1/2. That makes sense, but if you look at y1 minus y2 divided by 2, it's nothing but on geometric axis. So while this appears right, the function here takes a beating because the center of mass, we said, is the boundaries, the two boundaries. So if this was y1 and extending it to y2, what would I get? It's really that space, assuming the xy axis, this is x and this is the y axis, and it's the midpoint here. How do I calculate the midpoint? Is it really y1 minus y? The way to do the midpoint here, the value of this y1, the value of this 2 divided by 2 is actually y1 plus y2 divided by 2. So watch what happens. That function is not accurate in this case. This works very well if it was y1 and y2 were both positive, then I could subtract them. But for any general condition, it's the average. I hope this is clear, right? So in this particular case, this might not hold. I would have to write this as the integral of, for the area, I'm still good with its length, right? The length is basically, you wouldn't add this and add that. So the length is, I'm good with the length. So I'm good with the y1 minus y2 part to write my dx. But I'm not good to now say that my center is y1 minus y2. It appears good here if this was, if this was y2 and if this was y1. I could say y1 minus y2 divided by 2 makes sense here, but not generically. Generically speaking, it's the mathematical mean. So in this particular case, the correct equation would be y1 plus y2 divided by 2. Of course, the whole thing divided by RH. So just so you know, that's not right. The correct representation is this, which if you tweak the algebra, 0 to h, just before I don't, so I don't forget the limits, and then I'll take my RH out, it's 1 by RH, and I have my 2 out, so the 2 comes out. y1 minus y2 and y1 plus y2 is nothing but y1 squared minus y2 squared dx. That becomes the way you would have. When you have two functions and you need to find a lamina with boundaries in x and the y boundaries in y1 and y2, y1 being f1 of x and y2 being f2 of x, that becomes how your y bar function, of course this is divided by the integral for the mass, etc., etc., but essentially what used to be 1/2 y square is now written as 1/2 of y1 square minus y2 square. This is very, very important. Plug in the value, see what happens in that particular special case, and you can see here it's 2RH. This is nothing but writing these two because we have a positive value. If you do y1 minus y2, each of them are squared. So if you just do the math right here, without even doing the integration, I could just write r squared, h squared, x squared minus, again, there is a negative, but I'm squaring it, so it's positive r squared by h squared and x squared and dx, and the rest is straightforward. It's 0, so y bar is 0. What I'm trying to now bring you to is the concept of symmetry, and if you see symmetry, you know very well that, hey, around a symmetrical x-axis, the y-intercept of the center of, the y-value of the center of mass would be 0, which means you only have an x-intercept an x value for the center of mass, and that obviously we figured out how to calculate. So again, important idea here: when you get a lamina, do look for these things, because this is the hack. You see, if you see a line of symmetry, you know very well you can and justify it in the answer, saying there is a line of symmetry along the x-axis or the y-axis, and correspondingly either the y value of the center mass or the x value of center mass, depending on which axis, becomes 0, and then you're only solving one integral equation for the x or the y, depending on how it's positioned. So this is very important. And if you get two functions, remember, this is the mathematical representation. Even if you're tempted to do this, avoid it. This is how you do it. The rationale is given. So remember this. I've just extended this formula. The same thing could be there if you flip the x and the y, and if it was along the y-axis, like an upward, if it was like a inverted pyramid, facing upwards, then of course these would be in the x. But you have the same fundamental idea here that you need to change this to the square and not the whole square. So that's the idea here. So hopefully this clarifies. I'm going to take this off, and now I'm going to get to a couple of more ideas, just staying on this same topic of laminas, just so you see how you present the integration problem and remember the limits. Okay, so I'm back now, and let's see how we extend this a little bit. So we saw this idea here. You have a function y equal to f of x. We're good with that. Suppose we had another function y2 is equal to f2 of x. So you know that too. And you have boundary conditions here. You have your limits. So you've set your problem up really well, which is fantastic. But I want to just extend this now and say, hey, how do we take this? I mean, does this work for every case? Well, remember, I'm gonna do this first with a simple case that says, if I gave you a single function y is equal to 4x, right, which would be effectively a line something like that, right, and I gave you another function, right, y is equal to, let's say, the square root of what's a nice square root? The square root of 16 minus, say, 4x. So if I look at this very easily, I know that, hey, if x was 4, this would be, y would be 0. So if at some value of x, it would come to 4, that would be the case. And I know that if x is 0, y is equal to 4. So it pretty much looks like a circle here to me, and it would probably be something to that effect. Right now, I've just created this on purpose to make life easy for me. This could be 32 minus 8x squared or whatever, you could be anything. But what I want to illustrate here is this. And obviously it looks like my favorite pizza slice, but before I get to pizza slice, I want to just illustrate a fundamental idea here. What would happen if you attempted to do this problem using the integration and you set yourself up, and obviously you set yourself up with the integral equation for x bar, and then you have your beautiful integral here, and you say, oh, well, here's my two boundary conditions where x is 0, and then I have a boundary condition x is equal to 4, and I set up x equal to 4. How would I define the function inside? Because an infinitesimal rectangle is great, but that infinitesimal rectangle's its thickness is dx, that doesn't change, but its y value here was that function, and when it comes here, it's that function. So really this problem has to be set up, and this is why I talked about limits. This is two pieces. You'd have to set up your problem in two different pieces. You'd have to do this problem as an x bar that is integrated from 0 to some value here. Again, the way to do it would be equating the two, and if you wrote that as 4x, it'd be 4x squared is equal to, 16x squared is equal to 16 minus 4x. You'd solve for a value of x, which would then give you you'd basically get the point where these two meet, and usually because of the nature of this, you can tell it's a circle, and it would ideally come back and meet. You get two values. Take the positive value of x. So find the x, right? First, find an x. that is an intersection, that is an intercept between these two lines. So this is y and 2. Geez, something with my colors. Find x intercept, right, between y and 2. Identify that intercept, do a 0 to the intercept xi with y in here, with y1 here, right, and then add to that the xi to your upper limit for the second y, right? So when you do this, keep this in mind. I'm not going to do this for you, but you can attempt this classic problem and you'll see what the answers look like. What I am going to do though, because I have finally got to my pizza slice, I'm going to get to my pizza slice and kind of describe the pizza slice a little more and see what we can do with it, right? And also show you what the manipulation of that pizza slice means. So pizza slice drawing here, I drew the pizza slice like that, and maybe to make it. So if I was given this pizza slice and I was given theta, right, this makes it a little bit hard, because what will happen now if this is my x and y, where this gets a little hard is really, if I attempt to work on this, I have these two functions. Obviously, I would do two integrations. Same when I do my equation for y, because I have a 1/2 y square in the numerator, but my limits will continue to be 0 to an x-intercept and 0 to an x-intercept to another value of x. Right, so it would still be a complicated integration, but now that if I know it's a semicircle, there is one way I can simplify this, and the way I want to do it is, show you the approach is by saying, if I rotate this a little bit, in such a manner that my pizza slice is now making theta by 2 on each sides. Right? If I do that, then I can actually start working on this problem in a little different manner, right? So my approach now would be a little bit different, and let's kind of take this approach and see where we go, right? And the idea I'm trying to illustrate to you is, because I don't want theta, I'm going to do alpha, and here's what I'm going to do for you, and you can work the math out, but here I'm going to think of this very differently. I'm going to do this, and I'm going to define an infinitesimally small. So if I had my theta coming here, and if this was r, what would my setup be? My setup would be, again, these problems are all about how you set it up, right? Because you guys will know the integration. The setup for me is defining this small space here, identifying its center of mass, and then performing the integration. And if I do that, see how the equation changes here, because all of a sudden I can free myself up from the x and the y and look at it from an angle perspective. So I set myself up in, I will use blue this time just for contrast, and I will set myself up for that, right? So this is my tiny infinitesimal area. So if I do this, there are a couple of assumptions that I make. First, for my super tiny area, let's say I define that super tiny area. So this is theta, and the super tiny area is delta theta. So when theta tends to 0, what happens here is, we know for any angle, the arc length, right? This arc length is radius times, colors, radius times delta theta, right? And I can safely assume that at very, very tiny delta theta, this is a straight line. So I've got the straight line, I've got r on both sides, right? I have an r and an r, right? Which means I have a very simple and nice isosceles So this is r delta theta, and this is r and r, and the isosceles triangle. And if you do your geometry, you know that the centroid is 2/3 the way, which means I can safely say for this particular value here is 2/3 of r. If this is 2/3 of r here, and this is theta, then this distance is 2/3 of r cos theta, r cos theta, and this is 2/3 of r sine theta. Because this distance is 2/3 of r, because we know here that this is 2/3 height. Because these are so small, delta theta is so small that these values of r don't change. That is the assumption here. So we've created a tiny strip. The elemental strip in that case was a rectangle. In this case is a small, super small triangle. And then everything else in the math is basically the same. If I was going to find out the area of this, half base into height, pretty similar. Half base times height is r. I'm going to write d theta. So you can easily write r, half r squared d theta would be the area. If I multiply that with the rho, I have my mass function, which is basically an integral 0 to theta, because here I'm working with theta. Right, this is theta. So I have written that. If I want to do my xi mi, it's very easy. Again, I would do what? I would write my integral 0 to theta, right? And I would define my factors as same thing, mass of this, so it's the tiny rho, the area, r squared by 2, d theta, but the xi this time is nothing but 2 by 3 r cosine theta. So you can see how the integral function has changed here. This is mass, so this is the function, this is the part for mi, and this is the part for xi. And likewise for the sine value, you can write this. Play with it, and I think you'll see what's going on. But here's the other part that is interesting in this. Do I want to find a y and then I want to find out this part, or can I now say, hey, I have reasonable amount of symmetry, I'm fairly confident I have symmetry, I can now say that my y-intercept is 0, accept that, and only try to solve for x. If that would be the case, what would happen to my integral function? My limits change from negative alpha to positive alpha, right? But the factors inside don't change, which is r cosine theta, 2/3 r, doesn't change, right? And the infinitesimal area doesn't change either, which is 1/2 r squared delta theta. These don't change, right? So you're going negative alpha to positive alpha, and you can easily identify because cosine 0 to something, and then on the other side it's 0 the negative way. Cos of negative alpha is nothing but cos of positive alpha. When you substitute, it doubles the value. This half disappears. You're left with a 2 by 3, and if you remember the cosine theta integral, the integral is the sine theta, and if you remember, it's 2 by 3, and then you had an r, and then you had the sine alpha, and then you had the by alpha. If you remember the formula, you can arrive at this formula. I'm not gonna play with it now, but easy for you to substitute values, do the integration, and you'll arrive at this. So that's one of the ideas I want to establish to you, right? Using calculus. So you don't always have to do it with your y integration. You have to choose how you play with it depending on your function, and then you could do it by theta. But now let me extend this a little bit and see what else we can do with it, right? So now I'm going to ask you this problem in a little different, in a slightly different manner, and say, hey, I have a framework, right? This is my frame, okay? This is my frame, but wait, no, that's not my frame. I'm going to say I have a framework which is bent such that it subtends a radius of r and has equal angles alpha on either side. Now, we know that if we just had a simple framework, it's just basically a rod where we're not overly concerned about the area and it's only the length, and we have a density factor, we multiply that with the length, we kind of get the mass of the object, and we know pretty much, because we don't have too much to move on the x-axis, it's basically the center, and for any of these things, they're it's L by 2, right? So if this was L by 2 and this is L by 2, pretty confident that that's where it will be. We'll just say that the x value would be r at the center. But now that I've bent it, what's happening? So now let's take a look at this problem and say, how can we do this? Now you could go back to integration. There's two ways to do it. You can attempt it. Go back to integration, take out this piece, right? And take a very tiny infinitesimal piece here. Because it's delta theta, you would basically get S is equal to r theta, r d theta. You're not going to do area here because it's length. You've got your density factor by length. Your mass in the denominator is not by area, it's by length. It's density in length for the whole thing, which is L, or S is equal to R2 alpha. 2R alpha would be at the bottom. So you'll get that. And you could do this as an integration problem, or you could attempt to do it in a slightly different manner, which is to say, hey, if I have this setup, right, with R, can I assume it to be one lamina, right, of radius R, and another identical lamina, this time I have to use another color, right, an identical lamina of radius, let's say D. Where the conditions of alpha haven't changed. And what you can see is a subtraction. If I took this big pizza slice and carved out this small, I would get a small one. And then as it became smaller and smaller, as D became larger and larger, and D approaches R, I would get this very tiny strip, which is really this. So I could do this problem that way and see what happens to my function. So whatever happens here, if my x bar, so what I would do is, and I want to use the principle of moments and show you what's going on. So here I have some x bar. Now I told you that it is here the x bar is r times sine alpha, and I said this in the core concept by alpha. But here I said for a mass, and I write this in their respective color, the big one, he's got 2/3 r sine alpha by alpha, and he's got, the yellow, 2/3 d sine alpha by alpha, right? Now if you look at their mass factors, it's pretty easy to say that a larger area, so this one would be pi r squared by, if I just did an area of a circle, it would just by saying r2 alpha times r, so it's 2 r squared alpha, and with the factor of pi, because then if pi is equal to 180, you'd effectively get or pi is equal to, if it's 2 pi, you'd have a full circle which is pi r squared. So if I use that as a factor here, I could define a ratio between their masses. If I use this idea, and I want to just extend this so you get this concept, it's like a hack in an exam, no matter the area, if you apply a moment's principle, and what we will do is, let's say, we will define here, because I need another color and I can't afford to live without another color, I'm going to use this as this white color here, and I'm going to define the mass here as m. Here I'm going to define, using my orange color, for a mass in that one. So I'll just say m with r. Here m is with m, say, length, right? And for yellow, overlapping, but just so you have an idea, this would be an m with d, right? And if you really think about it, you could write the equation for moment as, maybe colors, m of L times this x bar, because this is for the wireframe, and you could write this as equal to my big guy here, the big one, m of r times, this would be 2 by 3r sine alpha by alpha, and the cute part here is this, subtracted by m of d, 2 by 3 d sine alpha by alpha. Now you can see very clearly, and you can do the math yourself, sine alpha comes out, the 2 by 3 comes out, this becomes r by d, but you'll also have a ratio for the masses, and if you look at the ratio of the mass, how we calculate the mass here, you had the r factor for the mass in the denominator showing up, right? So when we did the area, you're basically doing the tiny layers, you had r squared delta theta, it was the delta theta that got integrated. You basically took the r squared delta theta, which is r times that by half r squared delta theta, and then you integrated that for the whole mass, which kind of gave you 1/2, and then the r squared integral was r cubed by 3, and then here you would get d cubed by 3. If you substituted those in here, you could adjust these values, and you'll see what happens. You'll get the 3 on the, you get 3 by 2, and that factor cancels the 2 by 3 effectively, and as d is equal to r, because you're d approaching r to get this wireframe, as d approaches r, you'll see that this will basically reduce down to, and this is the math, this is quite beautiful, but you can do it. This will basically, with the masses all substituted, this here the mass just becomes r times 2 alpha, right? That becomes r times 2 alpha. This comes back, you'll get the alpha component on that side as well, and you will basically get, this would be, if I brought this out, you will basically end up with ml times r, and here you'll have sine alpha by alpha. And this is the math you can play with. It's quite interesting because you'll find a cube d cube minus a r cube minus d cube that will appear when you do the multiplication. D and r will stay as r minus d, and then you'll have another you'll have a square value coming in, and you can adjust them creatively by doing it as r minus d and r plus d, and play with the math a little bit, and then you'll arrive at this wonderful simplification because of the way the masses get calculated. But this is the extension of the integration problem. And I think with this, I'm going to say a lot of material on center of mass for uniform lamina, all using calculus. Fundamentally, remember, define the boundary functions in y, define the limits in the boundaries of x, this way or that way, doesn't matter. And then when you get something like a pizza slice, Remember, there's not always an integration in x. Sometimes it's efficient to do an integration in theta, and sometimes also worth moving around this so you see where the x bar is, and make the argument that because of symmetry, you don't need to do a y coordinate of the center of mass, right? So there's fundamental ideas here. A lot of the math is very interesting to play with. Very simple math as long as you know how to do the arithmetic or the algebraic manipulation. They are quite beautiful and the results are quite good. So I will see you in the next video where we'll extend center of mass to solid objects, and really it will be an extension of the two-dimensional plane into a three-dimensional object. See you in that video.